to introduce series and then we're going to take our break. An introducing series requires my beautiful piece of yellow paper. So I want you to flip over to 11.2, which is on page 117. Put it over here. Erase my beautiful Fibonacci spiral. Before I talk about 11.2, what's the sequence that we've been working with? What is a sequence? We were just doing sequences in 11.1. We just finished. What were they? Here's an example. Well, we didn't list very many of them, but here's examples of sequences. What are sequences? Yeah, just a list of terms that have an order, so it matters which order they come in. An ordered list of terms, a list of numbers that's in order. Okay, a series, people interchange those words all the time, is not exactly the same. It's not exactly the same. A series is defined to be something else, and I'm going to use my beautiful example here to talk about what a series is. That's what 11.2 is all about, series. Pretty much the rest of chapter 11 is primarily about series, but we also will be talking about some sequences within there. So let's take this beautiful piece of yellow paper here. Say I measured it, and whatever units I'm using is 1 by 1. Whatever it is, 1 by 1, I don't know what they are. My little, short little cute ruler, princess ruler, is 1 by 1. So what's the area of this?
1 squared.
1 squared, which is still 1. This is a 1 by 1 piece of paper, the area is 1. Area is 1. Okay, good, that's a good introduction. We're going to write some of these numbers in that space you have at the top of your page there. Area equals 1. Okay, so I'm going to take my beautiful yellow piece of paper, and I am going to cut it in half. And hopefully I'm going to rip it nicely. What's the area of this guy?
1 by 1.
1 by 1 half, right? So the area of this is 1 half. I'm going to leave that one there. The first one was 1 half. And then I'm going to take what's left, and I'm going to rip this one in half. Pretend it's square. I'll cover that part up. What's the area of this one? 1/4, right? Because it's 1 half by 1 half now. 1/4. And I'm going to put it on top of this guy. So this guy's 1 half, and this is 1/4. I'm going to put them together. And I got this little piece left. Guess what I'm going to do with it? You're a genius. I think that's a good idea. I'm going to rip it in half. So this was 1/4, remember. When I cut it in half, I now have 1/8. That's 1/8. I'm going to add it to my pile. I got a half, a fourth, and an eighth in that pile. Any suggestions on what I should do with this? Rip it in half. I like it. Good plan. Rip this one in half. I don't have it stored already. Let's put the wrong one in. Rip it in half. The area of this guy? 1/16. Okay? I'm going to keep ripping these. And I'm going to eventually have to get out my tweezers and my little tiny perfect scissors maybe, because the next one's going to be an area of 1/32, and then the next one's going to be an area of 1/64, and then the next one's going to be 1/128. I'm going to write these down here in a second. Maybe I better catch up. So I'm just stacking those up. Well, now this guy 1/128, and I'm going to cut him in half. And 1/256, and I'm going to do this forever. To the point where I need my microscope, and I need my perfect little tweezers and my steady hands, and I'm going to just keep ripping it and stacking these all up and do this forever I will never run out of paper. There will always be a little tiny piece left for me to cut in half perfectly, of course. And then I have this stack of papers here that forever stack up. What is the area of all of these combined? 1. You agree with that? All of these combined add up to 1 because it's the whole piece of paper. If I take that first one, which was a 1/2, and add it to the 1/4, and add up all these pieces forever, you agree that all of those add up to 1? So this is an infinite sum, a sum that goes on forever that actually adds up to a number, which makes no sense. It kind of blows your mind. How can you add an infinite number of numbers and get an answer? Right? I add an infinite number of fractions and I add it up to 1. This is what a series is. A series is a sum of your terms. A sequence was a list of terms. A series is a sum of a whole bunch of terms. And then a series might converge or diverge. Meaning, in this case we'll talk about it coming up, a series might add up to something, or it might go off to infinity or not add up to anything. Same kind of reasoning. Now, most of you in your mathematical career, probably since, I don't know, maybe 5th or 6th grade, have seen infinite series before and just didn't realize that's what they were. Where have you seen things that go infinitely on forever? Maybe even in 5th or 6th grade. How about this? 1/3 plus 0.03 plus 0.003 plus 0.0003 gonna run out of the room here pretty soon. Maybe you didn't see it like this.
1 divided by 3.
Yeah, this is really 0.33333, right? I just keep adding more 3's onto the end, and they go on forever. You guys all know what that is. Let's say this is 1/3. You've seen infinite sequences, infinite series before. You just didn't notice what they were. Right? 1/3 is an infinite series. You're adding all of these terms up forever to get 1/3. Not all series have a sum. If I add all the perfect squares, what's going to happen? Infinity, right? It just keeps infinitely large. So this series doesn't have a sum. Some series do. Like this adds up to 1. This adds up to 1/3. Throwing things at me. That's all it is. This one doesn't. So we'll do some more terminology and more investigating series after our break. Questions on the difference between sequences and series? What is the difference between a sequence and a series?
Just the ordered pair of numbers, right? And then this one's just the sum of numbers.
Beautiful. One's an ordered list of numbers, and one is the sum of an ordered list of numbers, right? You still have the first term, second term, third term. So the terms themselves are kind of like the sequence. The big difference is with a series, you're adding them up. And you've actually been working with them your whole life and just didn't know. Okay, let's take a 10-minute break. We'll come back and do some more with series. Let's talk some more about series. Yay, enthusiasm, great. Let's make sure we've got notation down. So we just started with my examples here of what some series are. And the next thing we talk about are the, what we call partial sums. So I want to make sure you understand some notation. This right here was the first term. So just like in a sequence, we call this A1. So whether it's a series or whether it's a sequence, it's still the first term. And this is A2, this is the second term, and this is the third term, so that hasn't changed. The A sub whatever, A sub n, just tells you which term we're talking about. But now we're gonna talk about partial sums. For example, S3. S3 is a partial sum. It's not the sum of the whole series, it's the sum of the first three terms. So S3, I just picked 3 to begin with, is the sum of the first term plus the second term plus the third term. If I wanted S5, that would be the sum of the first 5 terms. This is called a partial sum. And these are just terms. Okay, what I mean by a partial sum? I didn't hear you.
It's not everything, right?
No, it's just a certain number of
So are
terms.
these gonna be our bounds then?
What do you mean by your bounds?
Well, we're gonna put in those sums and we'll actually.
We're gonna get to an integral, we're actually gonna get an integral a little bit later. What's, the reason it's actually slightly different than an integral is an integral adds up everything along the x-axis, you know, like say from 0 to 2 or whatever.
So,
But when you're doing sequences or series, you're just doing the whole numbers, just at 1 and just at 2. Nothing happens at 1/2. There's not a half term or a 3/4 term. So it's like integrals, they're directly tied to integrals, but they're not exactly integrals. But it's here's the difference. Let me draw a picture for this. I'm glad you asked now. No, he's not glad, he's really sorry he asked. So let's say you're talking about this function right here. The integral, say, starting from 1 to infinity, would give you this total area in here, right? The integral would. But the series only adds up this number plus this number when I get to 2, plus this number, plus this one. It makes them look more like this rectangle, right? Plus this rectangle. Rectangles. Because this is, whatever the height is, say it's 1. This is a 1 by 1, and this is a 1/2 by 1, and a 1 by 1. So it's similar to integrals, but everything is squared now because we're only just talking about the whole numbers.
okay.
So they're directly related. We're actually going to talk about that after the exam next week. The integral test is actually something that's going to help us decide if a series converges or not, but they aren't actually integrals because they don't have nice smooth bounds. They jump from 1 to 2 to 3 to 4. Okay, partial sums though. We're talking about partial sums. What we want to do is list the first 4 partial sums for this series. Oops, I don't want the whole total. For this series. So the directions here says let's just add the term. So if I want S1, that one's kind of weird. What do you think that is? 1/2, there's nothing to add, right? S1 is the same as A1, so that's just 1/2. S2 is A1 plus A2, the sum of the first 2 terms. 1/2 plus 1/4, 3/4. Agreed? S3, did we do 3 already? Oh, we just made it, I wrote it up there, we didn't actually do it. The sum of the first 3 terms,
70.
you're good, so I'm gonna add 1/2 plus 1/4 plus 1/8, which is 7/8. This pen is dying. Find the 4th one, and go ahead and find the 5th one too. Find the 4th one and the 5th one for this particular example right here. What's my red? There we go. Everyone clear what you're doing? Adding up 4 terms, adding up 5 terms. What do we get for S4?
15, 16.
15/16. and S5.
31, 30 house.
Say it again.
31, 30 house.
31, 32. Beautiful. Any questions on where those came from? We're okay there? So these are the partial sums. So if you add the first term, you add 2 terms, you add 3 terms, you add 4 terms, you add 5 terms. What I want to do now is list those partial sums in a sequence. Oops, I can't draw a little bracket right now. Watch our notation here. I want to list, I'm going to write it out here, the sequence of partial sums. So what's the difference between a sequence and a series?
The sequence is just the order of grand numbers, and the series is a order of grand numbers, except the sum of them.
Beautiful, except it's not a pair, it's a list, but you're right. So the sequence is just a list of numbers and the series was the sum. We got these partial sums by adding some terms, but now I just want to list the terms. So the first term added up to 1/2. The first 2 terms added up to 3/4. The next one went to 7/8. The next one went to 15/16. And we went to 31/32. And it keeps going. This is a sequence of partial sums. The question I have for you is, does this sequence converge? Does this sequence converge? This goes back to what we talked about with sequences.
Reduce it to 1.
Converges to 1? How can you tell?
Just looks like it's gonna always be 1 less than whatever's on the bottom.
Okay, so he sees that the top is always 1 less than the bottom. Like whatever the bottom is, this is 1 less. That's always 1
Be
less.
like 107 over 108.
Yeah, so when you get really big, 107 over 108 is a lot closer to 1. When you get to 9999 over 10,000, it's even closer to 1. So it looks like it's going to 1. Do you agree with him? Maybe we can come up with a formula for this sequence. So we see the pattern that the top's always 1 less than the bottom. What's the bottom always doing?
Doubling.
Doubling. Multiplying by 2. All of these denominators are powers of 2. So do you agree that maybe my general term on the bottom is 2 to the n? 2 to the 1, 2 squared, 2 cubed, 2 to the n is general. How does the top compare to that?
N minus 1.
Close. It's not just n minus 1, it's this number minus 1. So it would be 2 to the n minus 1. This right here would be our general Sn. Meaning, if I want to go add 10 terms, 10, 1, 2, 3, 4, 5, 6, let's say 8, because I got 8 of them. If I want to add up these 8 terms, these 8 terms right here, if I want to add them up, I know the denominator is going to be 2 to the 8th, and the top's going to be 2 to the 8th minus 1. 2 to the 8th happens to be 256, so the top number is going to be 255. Because we found the pattern here. Now, what is the limit of 2 to the n minus 1 over 2 to the n as n goes to infinity? Make sure I'm a little bit sloppy with my handwriting. Make sure that you realize that there's a difference. I'm going to write this bigger in another color. I realize that my handwriting is a little sloppy, I don't have lines. 2 to the n minus 1 is not the same as 2 to the n minus 1. Which one am I supposedly writing over here, trying to write correctly? I'm on the left, right? This is what we're working with. Make sure you're clear where your minus 1 is, right? We're subtracting 1 after we find that power, not from the exponent. Sometimes our exponent has a minus 1 in it, so we have to be careful. So what's the limit here? It's 1. The quickest way is to just look at the highest powers. in the long run, the highest powers are gonna prevail, and 2 to the n over 2 to the n is gonna equal 1. So because this limit exists, that means the more terms you add, the closer the sum gets to 1. The more terms we add, the closer the sum got to 1. We actually knew that from earlier because we started with that 1 by 1 piece of paper. So what's this statement that's in your notes here? You flip over to, I'm going to skip over some notation which I'll go back to. On the top of the next page it says, so the sum of a series, so the top of yours, my notes are sometimes off a little bit. Top of page 118 is starting to show the sum of the series. So the sum of the series, that's what they add up to, is the limit of the sequence of partial sums. These were our partial sums, adding up to 1 term, 2 terms, 3 terms. We wrote it as a sequence, and then we took the limit of that. And whatever that approaches is the same thing that the series approaches. Because the limit of partial sums is just saying if you add more and more terms, what's it getting closer to? And that's what this says. If you add more and more of them, what is it getting closer to? It's really important that you know the difference between A3 and S3. What is the difference between A3 and S3? In your words.
A3 is just 1 term, and S3 is the sum of 3 terms.
Nick is all over this. A3 is just that 1 term. 1/8 is A3, the 3rd term in the list that we're adding. That's the 3rd term. S3 was the sum of the first 3 terms. So S means sum, right? Make sure you understand the difference because they're going to keep getting interchanged. Okay, let's flip back to the previous page. I skipped over some notation. Okay. So here's some definitions. You got a question?
I was just pointing out, I don't know, I didn't write anything down, I didn't realize that.
Oops.
Everywhere.
Well, you're gonna copy down Jake's later, maybe?
Maybe,
That'd be a good idea.
he's got pretty bad handwriting. Yeah.
Sometimes it's good just to listen, but then it
Well,
also.
everything makes sense, it's just, I just didn't realize that we were
That
like
you-
going
that-
with the notes, I was confused for a second.
Oh, you thought I was just creating my own thoughts here? Okay, so the definition of a series. I'm about a little bit below the middle of page 117, right? That's right about the middle. A2 plus A3. If you add up an infinite number of terms, which is what we've been doing, so these are just whatever the general terms might be, we write this with this notation here. We end up using K. By the way, they'll switch back and forth from K's to N's all the time. K equals 1 to infinity of a sub K. You need to also be familiar with this shorthand notation. This means start counting with 1 and do A1. And then you plug in 2, so you'll have A2. And then you plug in 3 and you'll have A3. So start with 1, keep plugging those numbers in. This means add them up forever. So that's exactly what this means. A1 plus A2 plus A3. For those of you who aren't familiar with that notation, say I have something like this. This says start with 1, keep increasing until you get to 3, then you're done. And every time you're going to plug in your K value to see what the term is. So in this particular example, the first term would be 1 squared minus 5. The next term would be 2 squared minus 5. And the last one would be 3 squared minus 5. And I'm done, because this one said start at 1 and stop when you get to 3. There's some that say start at 7 and stop when you get to 12. Could be anything. Most of ours will start at 1 and go to infinity. Sometimes they'll start at 0 and go to infinity, but not always. And then we would just find each term. So this is -4, this is -1, this is 4, so this adds up to -1. This whole thing equals -1. Just want to make sure you understand what this notation is. Just add up all those terms, however many you have. Most of ours will be infinite. So that's called an infinite series. Right underneath there is the definitions of the partial sums that we just talked about. A1, A1 plus A2, so forth. Notice this notation. Sn equals the sum of k equals 1 to n of a sub k. What does that say? It's almost at the bottom of your page, not quite, there's some stuff in between there. Yeah, you add up all the terms that go up to, in this case, the nth term. This is the notation for the partial sum. Remember, like we just talked about S3 over there? If I want S3, I'm going to start at 1 and stop at 3 and add up all those terms. S3 is A1 plus A2 plus A3. That's what this says. Start at 1. If I want S3, I'm going to go from 1 to 3, starting at 1, plug in 1, plug in 2, plug in 3. Again, the notation is the hardest part of chapter 11. Once you get comfortable with the notation, chapter 11 is not so bad. When you start having it all spinning in your head and you can't tell the difference between a sequence and a series and a term versus a partial sum, that's when it gets tricky. Okay, partial sums? Make sure you ask the questions if you don't follow it. And then finally, at the bottom of page 117, it says, if the sequence of partial sums, the Sn, if the sequence of partial sums converges to a limit, then we write that the series is equal to that limit. So for example, this guy here. This series, k equals 1 to infinity, this is using k in our book. K equals 1 to infinity of all those terms. This series equals 1. It adds up to 1. Want to see that notation there? If that limit exists, the limit of the partial sums is the same as that limit, and that's how we write that the series converges to that number. And if it doesn't converge, then we say the series diverges. The whole thing is like our integrals we did way back when. Does it converge or does it diverge? Converge means it adds up to an answer. Diverge means it doesn't. If you add it forever, you don't get an answer. Maybe it goes up to infinity, maybe it alternates. Who knows? Questions? Just give you an example of a divergent series. Let me get rid of this pen because I don't like it. Here's a divergent series. Sum k equals 1 to infinity of -1 to the k. And my question for you is, why is it diverge, besides the fact that I told you it didn't? What'd you say? What goes to infinity? This? Okay. This one over here went to infinity also. This is an infinite number of pieces of paper that I was cutting up, right? Infinite number of terms, but it added up to 1. So the infinity is not enough. See what I mean there? So I also want to point out, and I'm glad you said it, not to pick on you, Nick. We'll use those words a lot. It goes to infinity. What's the it? Is it the number of terms? Is it that the actual terms are approaching infinity? Is it the partial sum? So when you talk about the it, you wanna try to be more specific, especially when you're writing things out for me. Yes?
That's because the sum would end up being zero. It was even.
If the sum is zero, then it converges, because to converge, the sum is an answer. So do you think the sum is zero? How could we investigate this series some more? What would I do if I wanted to investigate? Start looking at it. Yeah, Tiger? Yeah, start putting the numbers in and see what it looks like. So let's start with 1 and plug it in here and get the first term. What's the first term going to be?
Negative.
-1. Great. What's the second term?
Positive 1.
+1. -1 squared, right? +1. Plus, what's the third term? -1.
How does it keep repeating?
And it keeps repeating. It's an alternating series.
So if it's an alternating series, it's better than.
That's a good question. So he says, if it's an alternating series, it diverges? Not necessarily. This happens to be an example of an alternating series that diverges, but it's not because it's alternating. Many alternating series, which we'll see later on, do converge. How did we determine that this one converged? What were we looking at over here? What was the sentence at the top of the page? Top of the page 118?
This is the series is the limit of the sequence of partial sums.
The sum of the series is the limit of the sequence of partial sums. So maybe we should look at some partial sums and see what this guy's doing. What's S1? What's the sum of the first term? -1. What's the sum of the first two terms?
0.
0. What's the sum of the first three terms?
-1.
-1. What's the sum of the first four terms?
0.
Aha. So that's an S and that's a 5. Can you tell the difference? S and 5. That's -1. So if I list my sequence of partial sums, my SNs, make it a sequence now. This is -1, then 0, then -1, then 0, then -1, then 0 forever. What's it approaching? Good question. What'd you say?
And you said it's not really.
It's not approaching anything, right? You can't say the limit's -1 and the limit is 0. It's not approaching one number. So this limit doesn't exist. This limit doesn't exist, which means this sequence diverges, which means this series diverges. The only way it would converge is when you add more terms, you're getting closer and closer to a total. And as soon as you think you're at the total, like Joseph thought the total was 0, you add one more term, now you're at -1. And then you add another term, and then you're at 0. What's up, Nick? Does not. Thank you. Does not exist. Points that out. Thank you. Does not exist. I said it, didn't I? My mouth and my pen didn't agree. Does not exist. Everyone clear with that? Sorry about that. I'm glad you caught it. All right. So where was I? Did I get everything on there? We talked about converges and diverges. Converges means it adds up to some number. Diverges means it doesn't. It might bounce around like this one. It might add up to infinity like this example here. This one would diverge. Right? You just keep adding and this is not going closer to anything. This one's going to diverge. These two that I started with both converge. This one converges to 1. This one converges to 1/3. Pretty much all of chapter 11 is going to be, here's a series, does it converge or diverge? Pretty much almost all of chapter 11. There's a lot more to do besides that, but that's going to be the primary question all the way through. All right, so let's look at another series, which is a little bit messier. a new series, so I think I'll get rid of this guy over here now. Example 1, we're only finally to example 1. Wow, we have to do it over 2 different days. So example 1 wants to know, is this series, example 1, is this series, notice they switched from K's to N's, it happens all the time. You can use any variable for what we call your index. This letter here, sometimes it's K, sometimes it's N, sometimes they'll use M, J, they kind of just mix it up. Doesn't really matter. They want to know if this series converges or diverges. Is it converges? Question mark. And the first question I have next to that is, how do we even know it's a series? What makes it a series, not a sequence?
Summation notation.
Yeah, the summation notation right here, right? That tells you you're adding up an infinite number of terms. If it was a sequence, what would it have looked like? What would I have written as a sequence?
Just that right part.
Yeah, just this part here, 1 over n times n plus 1. And that would have been in brackets usually, n equals 1 to infinity. This one's a sequence. Asking if this converges is different than asking if this converges. Let's talk about that for a minute. Remember I said the notation's the scary part, overwhelming? This was a while ago. How do we decide if this sequence converges? The sequence. Good thing I asked.
Is it because the denominator is always getting smaller and smaller and smaller?
Yeah, well, the denominator's getting bigger, which makes the
Bigger,
fraction
yeah.
get smaller, you're right. And we're just looking at what do these numbers approach. So if we were to list them, the first one is, let's plug in a 1, that's the 1 times 2 in here. The next one will be a 2 times 3, so that'd be a 6. Oops, not pluses, sorry, sequence. Plug in 1, plug in 2. If I plug in 3, that'll be 3 times 4, so that's 112. And I'll keep going 1 more. Oh, where am I? 4. 4 times 5, that's 1/20th. Dot, 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 dot. So to ask if the sequence converges, we just want to know what these terms are approaching. What are these terms approaching?
0.
Right, these are approaching 0. Agreed? Because the denominator keeps getting bigger and the numbers get smaller. So this sequence converges because these numbers are eventually approaching 0. They're getting closer and closer to 0. This is a convergent sequence. Because the limit as n goes to infinity of each term exists. You got 0. Doesn't have to be 0, it has to be some number. A little review. What does it mean for a series to converge?
They all add up to a number.
They all add up to some number. Do all of these terms add up to some number? Do they add up to 8? Do they add up to pi? Do they add up to square root of 3? That's the question here. Do these add up to an answer versus does each term get closer to something? That's a totally different question. Both of those are going to get intermixed throughout chapter 11. So, how do we determine if a series is convergent?
Has to add up to a number.
Okay, how do we determine if it does?
Is that given to us, or is there, can we find that out?
Which is the that you're referring to?
The sum for this.
No, we don't know what the sum is. If we're given the sum, then we would know it converged, right? If it said, hey, this adds up to 7, then we would know the answer. So we don't know if it adds up to a number or not.
What if it has like bases headed to 7?
What'd you say?
What if it has like does this add up to 7? I think
Does-
That's what he's asking.
Oh, so is that what you're saying, Zach? Like, are they asking, does this add up to
Well, I'm
7?
just saying, if you think about it, like, you can take every number in that series and add them up to something. But does that something mean that it's converging, or?
If you get a something that's not infinity, then yes, it's converging. But you know, like this example I just did right here, we keep adding, and we're not approaching anything. We go 0, negative, we get 0, then we get -1, then we get 0, then we keep adding, but our answer keeps changing. Where the first example we did, we did the 1/2 plus the 1/4. As we add more and more and more, the answer's approaching 1. These aren't approaching anything.
Gotcha.
See the subtle difference?
Yeah.
So that's the question. If we add these all up, am I approaching something? Or am I alternating and bouncing around? Am I blowing up to infinity? We don't know. So the question is, how do I answer it? How do I determine what's going on here?
Can you do partial sum?
Aha, we're gonna look at the partial sums. What if I just add one term? What's the answer? These, by the way, the terms are listed over here. We started them.
1/2.
1/2. What if I add two terms?
4/6,
2/3.
Two terms is 1/2 plus 1/6.
4/6.
2/3.
2/3.
You guys are already way faster than me. That's 4/6, so that's 2/3. I can get that. I have to get it in my head. You have to get a common denominator. 3/6 plus 1/6. So if I just add one term, I'm at 1/2. If I add two terms, I'm at 2/3. If I add three terms,
9/12.
what's my third term? What'd you say? It's 9/12?
9/12.
3/12?
3/4.
Oh, it's 9/12, which is 3/4. I gotcha. You're making two things. Adding up three terms? Let's do one more for fun. 1/2 plus 1/6 plus 1/12 plus 1/20.
16/20.
You using your calculator or doing that in your head?
My head.
Impressive. 16/20, that's 4/5. So the question is, when you look at just these sums, just the sums, just these guys. Here's one term. If I add 2, if I add 3, if I add 4, what are those doing every time I add another term?
Increasing, getting closer to 1.
Increasing and getting closer to 1, he says? Could we write a general formula for Sn? When n was 1, we had 1/2. When it was 2, it's 2/3. When it was 3, it's 3/4. What do you notice about the numerator?
The numerator goes up by 1.
The numerator's the same, right? If you want the first partial sum, it's a 1. You want the fourth partial sum, it's a 4. Guess what it is on the nth partial sum? N. And then how's the denominator compare to that?
And plus
It's 1 more than that, it's n plus 1. So if I wanted to say add up 10 terms of this, that sequence, this series, if I wanted to add up the first 10 terms, I could add those 10 fractions. I could. Or I could say, you know what? S10 is going to be 10/11. See how I did that? We found this pattern and then used that. Easier than doing that sum of all of those. And so the question now, let's go back to the question we were asking. To determine if a series converges, we want to now look at this list of partial sums and see if it converges as a sequence. Listing these as a sequence, the partial sums. 1/2, 2/3, 3/4, 4/5, dot, 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 n over n plus 1. How do I decide if this converges? I get a number, and if I go out there infinitely, it's approaching something. But in general, I'm taking the limit as n goes to infinity of this. What happens if I do an infinite number? Where are they approaching? If you have the formula, it's easy to take the limit. What's that approaching? N over n, which is 1. So what this tells me is the more terms that I add, whether I add 1 term or 2 terms or 3 terms or 4 terms or 10 terms, the more I add, the closer that total is getting to 1. Does this series converge? What's it converge to? It converges to 1. Yes. It converges to 1. Because the more terms I add, the closer that total gets to 1. What am I going to get if I add 100 terms? What if I want to add 100 of these? Well, I won't get 1 if I add 100. Careful. If I add 100 terms, it won't be 1.
100 over 101.
Aha.
Closer to 1.
If I add 100 terms, it'll be 100 over 101. It'll be almost 1, but not quite. But close to 1. But if I could add them forever, I'd get 1. We're running out of time now before forever. It's hard to wrap your brain around the fact that something can be infinite and finite at the same time. I mean, that's the thing that's really hard. You're adding an infinite number of things, but getting an answer that's only 1. My paper, I'm going to have an infinite number of pieces of paper here. Some of them are really tiny too, see? They add up to 1. Even though I've got an infinite number there. I kind of cheated and didn't do all of them, but I was close. Questions? Brains are about to explode, I get that. We'll talk about the rest of it next time. I'm going to give you one more example to help wrap your brain around something that can be infinite yet finite. Not going to write it down, I'm just going to talk about it. So imagine that I, start right here. I want to get to that wall. I wish I could get there. But I'm only allowed to take 1 step at a time. And it has to be half, okay, maybe it's a hop, a jump if I could jump. I only can move halfway to that wall. Let's say it's, how far is that from me, think? 15 feet maybe? 15 feet? Close enough? I'm not very good at estimates. Let's call it 15 feet. So I might take a step halfway there. So, halfway there. So I'm over here now, I'm 7.5 feet away. I took 1 step. My next step is going to be halfway again. So now I'm over here. Halfway. I'm doing another step, I'm going to get halfway there. And I'm going to take another step, and I'm going to get halfway there. And then I'm going to go another halfway, run out of room, and another halfway, another halfway, and I'm going to keep doing these little tiny little halves forever. Will I ever get to the wall?
No.
Nope. But if forever could go on forever, do you agree that I would have traveled 15 feet? So if I could take an infinite number of steps, I would go a distance of 15 feet. The sum of all those steps would add up to 15. So, what'd you say?
Thank God we round.
Thank goodness for rounding, yes. Well, and remember this. We already knew that. That's an infinite number of 3's, and it adds up to 1/3, right? So we actually kind of already knew that you could have an infinite number of things that add up to a finite number. So we want to be careful when we talk about something being infinite. It matters if we're talking about an infinite number of terms, like an infinite number of steps, is different than an infinite distance that I'm traveling. Right? I'm not going infinite distance. I'm only going to go 15 feet if I could do an infinite number of steps. You want to make sure you can tell the difference there. How are we feeling about series? Say so? Notation's a little overwhelming. Make sure you go look at that notation and come back with questions. On Thursday, we're going to finish up the rest of this lecture on 11.2, and you're going to ask questions about the notation, and then the second part of Thursday, we'll go to review for that exam. So I'll see you Thursday with a quiz on 11.1. Okay? Good? Okay, let's pick up where we left off with 11.2. We left off with geometric series, which is in the middle of page 118. And the first couple lines, I'm actually going to skip over and wait till we get to 11.3. So I'm starting about halfway down the page where it defines a geometric series and actually has a formula that looks like this. A little bit more than halfway down the page. This is the definition of a geometric series. Page 118. Are we there? I know flipping pages for good. 118. So it's defined to be a geometric series. This is the definition. Here's my words for a geometric series. It's a series. Series just means you're adding a bunch of terms, right? Where each term you find by multiplying by the same number each time to get to the next one. There's what we call a common ratio. I think I gave you one of these last time. Well, actually, the one with the papers. We did 1/2 plus 1/4 plus 1/8 plus 1/16, where I ripped up my paper into a million pieces, right? Actually, it was an infinite number of pieces, to be more precise. What do I do each time to get to the next term? What am I multiplying by? 1/2. So we say this has a common ratio of, there's two separate words, just so you know. Common ratio of, I tried to use that O for two purposes here, of 1/2. So we would say R equals 1/2. So that is an example of a geometric series. A is just your first term. In this particular problem, A also was 1/2, coincidentally. They're not always the same. So A was 1/2, that's the first term. And then to get the next term, I multiplied by 1/2, A times R. So if I write this, it started with 1/2. This was 1/2 times another 1/2. Right? A times my R, they happen to be the same in this example, unfortunately. The next one was 1/2 times 1/2 squared. I started with A and multiplied by 1/2 two times. That was an example of a geometric. Geometric means you're always multiplying by the same common ratio to get to the next term. This is the shorthand way of writing it. It's the same thing. You start with, if you plug in a 1, you'll get A R to the 0, so that's this one. Plug in 2, you'll get that term. So it's a geometric series. The nice thing about geometric series is if you recognize that it's geometric, you can tell if it converges or not just by looking at R, your common ratio. So it converges if your common ratio, or the absolute value of it, could be positive or negative, if your absolute value of R is less than 1. Whatever you're multiplying by, if it's a number between -1 and 1, essentially, you're guaranteed that it will converge. Let's talk about why. So this one converged. Remember, these were all the little infinite pieces of paper that added up to 1, so we know that converged. Can somebody give me let's make up a geometric series with an R that's larger than 1. Let's just make one up. Who wants to be creative? How about a starting number? 3. Okay, I like it. Let's use A equals 3. Now someone pick another number for R. Something larger than 1. Anything you like.
4.
4. I like it. So if A equals 3 and R equals 4, the first term is 3. What's the next term? Common ratio means you are always multiplying, not adding, multiplying. So guess again what the second term is? 12. 3 times 4 is 12. And the next one? 48. You pause for a moment. This just means you're multiplying by the same ratio every time. So I multiplied by 4. I multiplied by 4. I don't know if I can do this one in my head. 192? Is that 48 times 4? Thank you. It's about as far as I'm going to attempt going in my head. What do you think these are going to add up to? Infinity, right? They're infinitely large. They're not going to add up to any number that we can talk about because these keep getting bigger. They just keep getting bigger. So as soon as your R is some number larger than 1, these terms just keep exploding. The only way it's going to converge is if your terms are getting smaller and smaller and smaller, that eventually they're so small they don't add up to much. Right, so that is why we have that it converges if the absolute value of your ratio could be positive or negative, if it's less than 1. Does that make sense? That's an example of a divergent geometric series. I can't stress enough that recognizing a geometric series is going to be your best friend for all of chapter 11. Knowing when you have geometric. Geometric is going to be the nicest one to work with. So what does it mean to be geometric?
Multiplied by the same figure.
Multiplied by R.
We're multiplying by the same R every time to get to the next term. So you want to always check for that, because if it's geometric, life is a lot easier. Okay, and here's the really cool news. If it's convergent and it's geometric, you can actually figure out what it adds up to. So the next line has that if you have any geometric series, it's going to add up to the first term divided by 1 minus your common ratio. Every time. Every time.
Can you say it again?
If you're trying to figure out what it adds up to, like we were trying to figure out what this added up to, we'd already done it earlier, it was 1. But we could say the first term is 1/2, the common ratio is 1/2. We could find the sum by taking that 1/2 over 1 minus 1/2 in that particular example. So the sum, we just call it S, would be the first term over 1 minus the ratio. They're not always the same, but in this case they were. Ends up being 1/2 over 1/2, which ends up being 1 in this case. But any geometric, you can figure out what it adds up to. Let me show you something that you already know in a different way. We talked about this last time too. Remember this decimal we talked about last time? And I said it's actually a series. It's equal to 0.3 plus 0.03 plus 0.03 and so on. My question for you is it geometric? And if the answer is yes, there must be a common ratio. I want to know what it is. Is it geometric? I heard yes. What's R then? 1/10 or 0.1? You guys are all saying the same thing. Yes is either 0.1 or 1/10. Right? Whichever way you want to write it, as a decimal or as a fraction. You're dividing this by 10, dividing that by 10. That's the same as multiplying by 1/10. What if you can't see it? What if you don't know if it's geometric and you can't see what the common ratio is? Like, this one is kind of obvious to find out what it is, right? How do you think you could find the common ratio if you're not sure?
Turn it into fractions.
Turn it into fractions, or just divide any term by the one before it to figure out what you multiplied by. Or maybe I'll take this term divided by the one before it to see what did I multiply by. So I could take the fourth term divided by the third term, and if I did that, I would get 1/10 or 0.1, whether you're working with fractions or decimals. And then you could see that the ratio is that 1/10. If you took this one divided by this one, guess what you get? Same thing. This one divided by that one. So if you have to do division, you can. Okay, so this particular fraction, we know that the common ratio now, I'm going to write it as a fraction because it's nicer to work with. I'm going to call it 1/10. What's the first term? What's A? 0.3, or if you want to work with fractions, because you like fractions, we call it 3/10. So there's the first term is your A, and we found our common ratio. Does the series converge? Yes? Why?
You said every geometric series converges.
Not every geometric series.
It is less than 1.
Oh, it's less than.
If your common ratio is less than 1, so I'm glad you said that. So because my ratio is 1/10, and the absolute value of that is less than 1, I know it converges. This one does not converge, right? Because R was too big. So if it converges, this will tell me what it adds up to. We already know what it adds up to. But the sum is equal to the first term over 1 minus the common ratio. You could leave decimals in there if you wanted to work these out. The problem with that is putting decimals inside of fractions, it's really hard to simplify them. Best just leave them all as fractions. So this is 3/10 over 9/10, which is 3/10 times 10/9. Three over 9, 1/3, which we already knew. But now you have a way to turn any repeating decimal back into a fraction. I know you can push the button on your calculator. But back in the old days, we didn't have calculators that could do that. You can take any repeating decimal, turn it into a fraction just by taking those repeating parts and using the fact that it's a geometric series. Even if it's repeating like this, like here's one that we don't know. 0.17, 17, 17, 17, 17. What do you think I would do there? I wanted to turn it into a fraction without using a calculator. Using geometric series, what would I do?
Over 100?
Yeah, there's gonna be 1 over 100. So I would break it up into each term, so 0.17, take the repeating parts, then it's 0.0017, right? And then it's 0.00017. So I'm pulling out each of those 17s basically. I'm keeping them in the right places. So here's my A. That's an arrow. Really bad one. There's my A. And Ilya's totally right. It's 1/100th or 0.01 each time to move the decimal over 2 places. And then you do the same thing like we just did, figure out what it adds up to. Now you have a new party trick to show off how you can turn decimals into fractions. I don't know what kind of parties you go to, but you never know, you might need this. Okay, so that's just examples of some geometrics. The nice thing about geometrics is you can just look at them and see if they converge. Look at the one on the bottom of page 118, example 2. I claim that we should be able to just look at it and see if it converges. Does this series n equals 0 to infinity of 0.9 times 0.1 to the n, convergent or divergent? First off, is it geometric? How do you know? Yeah, that exponent on the 0.1 tells you you're multiplying by 0.1 over and over and over and over again. So that exponent right there tells you that your r is 0.1. Because you're going to have 0.1 to the 1, 0.1 squared, 0.1 cubed. Every time there's another 0.1 that you're multiplying by. So because our r is less than 1, it's convergent. See how we found the r in there? So I have to start recognizing what the notation means. So the question said, is it converge or diverge? If it's convergent, find the sum. So now that we decided to converge it, let's find the sum. What do I need?
Your A and your R.
My A and my R. My first term. I got my R very good there. I need my A. My A is my first term. Now be careful, it's the first term, but where does this series start? At 0. So I have to plug 0 in to get the first term. This tells me to start at 0. So my A is 0.9 times 0.1 to the 0, which is just 0.9. It's not always just that number in front, it really depends on where your index starts. So the sum is A over 1 minus R, 0.9 over 0.9, adds up to 1. If you had written these terms out, it would have looked like this. 0.9 plus 0.09 plus 0.009. When I add those all together, that's this number right here. I just keep putting another 9 on there. If you list 0.9 forever, it's gonna end up to 1, right? Forever, you can't really get to the forever, I know. Same as 1, weird. Okay, so that one converges. Next page, 2 more examples. Let's look at these geometrics and decide if they converge or diverge. Just by looking at them, if we can tell the common ratio, let's just erase that formula, let me move it over here. The sum is A over 1 minus R. Example 3A. 2/3 plus 4/9 plus 8/27 plus 16 over 81. The question is the same as that last one. Does it converge or diverge? If it converges, find the sum. So what do we need to do? You're quiet today, it's making me nervous.
It should be 2/3.
First we have to find the ratio. Carlos already thinks he has it. Ratio equals 2/3? We agree with him? Multiply this by 2/3, you'll get here. Times 2/3, you'll get here. Times 2/3, you'll get there. So that should be enough to decide whether or not it converges. Absolute value of 2/3 is definitely less than 1. So it converges. So if we add all of these fractions here forever, what are they going to add up to?
Would it be 1?
Couldn't hear you, Joseph.
So would it be 1?
It won't be 1, because already 2/3 plus 4/9 is more than 1.
Just diverges to 0? No.
They won't add up to 0 because we're adding a lot of positive numbers.
Infinity?
Well, converges means it adds up to something that's not infinity.
Versus on 2.
It's actually going to converge to 2. If we add all these fractions up forever, it's going to add up to 2. Let's show everybody why. How am I going to find what it adds up to?
1 over, or 1 over A minus R.
A
No,
over
it's
1 minus R. You'll get them eventually. The A, the R, and the 1 go in there somewhere.
Yeah.
The sum is A over 1 minus R. As soon as we see that it's less than 1, then we know it converges, meaning it adds up to a number. And then we find it always by taking the first term, which in this case is 2/3. That's my A. A lot of these examples, the A and the R are the same, so be careful. A is the first term, over 1 minus A. 1 minus R, excuse me, I just said it backwards. 1 minus R. Contagious, Chad. We say what we mean, we mean what we say. 2/3 divided by 1/3 is 2. So that series, if we could add all those fractions forever, will add up to 2. How about 3B? 1 minus 1/2 plus 1/4 minus 1/8.
R is equal to 1/2.
R is equal to negative 1/2, right? Negative, because it's alternating. You guys see that? Negative, positive, so R equals negative 1/2. The absolute value of that is definitely less than 1. So this is convergent. Because our absolute value of our ratio is less than 1. What does it add up to?
2/3.
2/3 actually. The first term is 1, that's my A, over 1 minus my R, and R was negative. Right, R was negative 1/2. So this is 1 over 3/2, which is 2/3. I love this problem, because I'm a total nerd. You're adding all these fractions that have powers of 2 in the denominator. 2's, 4's are all multiples of 2. Right, 2, 4, 8, 16. You add up all these fractions forever that all have denominators of 2, and your answer ends up being 2/3. Where did 3 come from? How did we? I think that's so cool. They take all those even denominators and get an odd one when you're done. Yes, sir.
How do we know what R is?
So we're basically asking ourselves, what do you multiply by this to get here? What do you multiply by this to get there?
Okay.
And from there and so forth. And so some people can just look at it and see it. And if you can't, because sometimes it's easier than others, you can always just divide any two of them and see what you had to have multiplied to get there. Good enough?
Yeah, I just didn't know like if it was given to us or not.
Yeah, so a lot of times it's not given, you have to look at it and figure it out.
Okay, that makes sense.
It's whatever you're multiplying by, yeah.
I was thinking maybe it's because 2 over 3 is 0.666 repeating, and that's an even number or something.
Mm-hmm, yeah, something like that, yeah.
It made me think, that's been blowing my mind a little bit, the why 0.999 is 1, but
Uh-huh.
it's because that would then become 0.99999.
Right, yeah, I love that, this blows my mind too, like, how can all those 9s be equal to 1, but
Yeah,
they go on forever, it's like you round it at the end.
that makes sense.
Yeah, it makes sense and then it doesn't.
Yeah.
Questions on geometric so far? Okay, so the next thing on page 119 is this theorem on all these properties. And the notation looks scarier than it is, so I'm actually going to talk about the notation as opposed to really write it all out and stick with it. What that theorem says is that if you have a series with some constants in it maybe, you can just pull those out front because they're not going to affect what happens. For example, if I was adding 3 times 2 to the n, for example, technically that means, 3 times 2 is a 1, plus 3 times 2 squared, 3 times 2 cubed, right? If I was to write it out. But couldn't I just take that 3 out front and do this? Because every term has a 3 in it, so I can factor it out. So the first property is if you have a constant in there, you can just pull it out front. Because you're going to be able to pull it out of every term. So a constant gets pulled out front. And the next two properties are that if you happen to have 2 terms being added or subtracted, you can look at the 2 pieces separately. Just break it up just like you would expect it would. Pull constants out, look at terms independently. I'm going to do the next property as we look at example 4. Example 4 looks scary. But here's the good news, it only looks scary. Example 4 wants to know if, can't read my writing here. I think every day my contacts have a different prescription. I don't know if that's true, but it sure feels like that sometimes.
Wouldn't it just be easier to wear glasses then?
Yes, but they hurt my nose,
They really do.
and I get headaches. What'd you say?
I said they really do.
They do. I cannot find glasses that are comfortable.
Contacts are way better.
What'd you say?
Contacts are way better.
They are. So I just kind of deal with the fact that I can't quite read sometimes, and if I get it just to the right spot, that I can't. But Glasses hurt. Other people wear them just fine, but I can't do it. When I get migraines, migraines is horrible. Okay, so here's example 4. If it converges, find the sum. Is it geometric? The only way we know how to find the sum is if it's geometric. How can we tell if it's geometric? Silence, definitely. How can we tell if it's geometric?
Where's the R?
What's the R, right? We gotta figure out what is the R. If there's some common ratio that we're multiplying by every time, then we'll know that it's geometric. So I think I'm just gonna start writing out a couple terms to see if I can find out what R is. I can't tell by looking at it. So I'm gonna start by plugging 1 into here. If I plug 1 into there, I'm gonna have 3 squared minus 2 to the 1 over 5 to the 1. I started with k equals 1. The next term, k equals 2, that'll be 3 cubed minus 2 squared over 5 squared. I plugged in 1, I plugged in 2, now I'm going to plug in 3. So that's 3 to the 4th minus 2 cubed over 5 cubed. There's the first 3 terms. I'm going to simplify those and see if I can figure out. 9 minus 2, this is 7 over 5. Someone's going to correct me if I make an algebra mistake, right? 7 over 5 plus 27 minus 4, 23 over 25. You guys agreeing with me, or we're just all being quiet today? You don't know? You see what I'm doing, or no? I'm just multiplying this out. You guys have calculators in your hands to double check me. No one's yelling at me yet.
So, 120.
You're good? I'm good? Thank you. Need someone to verify. 3 to the 4th is 81. Oh, 81 minus 8. 73 over 125. Okay. So the question is it geometric? And if so, what's the ratio? Yeah, I see the denominator's being multiplied by 5.
Yeah.
Is it 3/5?
3/5?
Yeah.
Let's try it. 7/5 times 3/5 would be 21 over 25. Not quite, because we need 23, but you're close. And if I multiply this by 3/5, I won't get that either. Common ratio is not so obvious here. So let's divide these two and see what you have to multiply by to get from here to here. If I take this term over this one, I'm basically saying, what's the ratio? What times this equals that? I'm just doing a division problem? You're not gonna like the answer. Oops, times 5 over 7.
Oh, that's big.
Yeah, it's big. The 5s are gonna reduce though.
Yeah.
It's 23 over 35. If I multiply this by 23 over 35, I'm gonna get this. You can check it if you need to. It will work though, I promise. What do you think is gonna happen if I multiply this by 23 over 35? So to get, let me put some notes on here. To get from here to here, R equals 23 over 35. So if this is geometric, what's going to happen if I multiply this by 23 over 35?
Should get 70.
I should get that. Guess what? Not going to happen. 23 over 25 times 23 over 35
It's 529 over 12.
doesn't even reduce. 529 up on top,
529 over 1225.
and it doesn't reduce, and it's not equal to this. So this going from here to here is some different R. So there isn't a common ratio, it's not geometric.
My bad, it's 875. What?
875, thank you for checking that for me, I'm just trusting you. It's still not any good though, it doesn't reduce to that, either way. So what we did is we were checking, can we always multiply by the same number to get to the next one, and it didn't work. It's not geometric. Bummer. So how do I know if it converges, and how can I find the sum? The only other way we had was to like do partial sums, which doesn't look like fun with these fractions, for sure. But I'm going to show you what those arithmetic properties tell you. Do we agree that this series, I love your algebra. How many times have I said that? Minus 2 to the k over 5 to the k. Do we agree that that's the same as, bless you,
Thank you.
the same as this? 3 to the k plus 1 over 5 to the k minus 2 to the k over 5 to the k. Is that the same? Yeah, just breaking up that one fraction into two fractions. That's what the arithmetic property is showing you. If you can have it with two different terms in here, look at each piece separately. So we're going to consider the first series minus the second series. Recall that's what the arithmetic property shows us? I want to start with this guy because he's easier. Is this geometric? Is this geometric?
Yes.
Yeah, what's R?
2
2 fifths, right? Because this is really the same as 2 fifths to the k. So every time you're multiplying by another 2 fifths. So this guy's geometric, R equals 2 fifths. It's kind of easy to see because it has nice powers of k. Is this one geometric? No? Maybe? No? Yes?
Because the k is being added on top.
Yeah, but watch this. Algebra is our friend. This numerator is really 3 times 3 to the k. K plus 1, right? Here's the 1. Oh, mind blowing. Man, I hear the light bulbs going on people's heads. We agree that numerator is equal to this? So is it geometric? Yeah, and the R is 3 fifths in this case, because it's 3 fifths to the k. 3 times 3 fifths to the k. Anytime you can write some constant raised to a k or an n, whatever it happens to be, that's telling you it's geometric. You can pull out extra ones all you want. Doesn't change anything. So R is equal to 3 fifths in this case. So does this one converge? I got one person nodding yes. Okay, I got about 3 people. Why? Why does it converge?
R is less than 1.
R is less than 1. Does this one converge?
Yes.
Yep. R is less than 1. So this one converges and this one converges. And so we're just going to find out, okay, what the heck does this guy add up to? And what the heck does this guy add up to? And then we'll subtract them and we'll have our answer. So it's actually 2 problems in 1. So for the first term, what's A? I better write those over there before I keep going. What'd you say? 3 fifths?
No,
For this guy, 3/5?
That's the first term, so plug K equals 1 and 2.
Okay, so I'm gonna plug K equals 1 in there, it's not gonna be 3/5 though, that's why I'm a little worried.
9 bits.
I'm gonna plug 1 in there. I get 3 squared over 5 to the 1. I plug the first K equals 1 in there. That's 9/5. So 9/5, and we already talked about its R. So we have our A and we have our R for the first one. How about this guy over here? We already found the R. What's A in this case? When I plug 1 in there for K?
2/5.
That's 2/5. I like this one because it shows you that A and R aren't always the same. So we have this A and R, and we have that A and R. So the sum of this whole series is going to equal, where's my first A? 9/5 over 1 minus 3/5 minus 2/5 over 1 minus 2/5.
45 over 10.
You already done the whole thing?
Oh,
Nice.
well,
I'll
that's
catch
the
up
first
to you in a
part.
second. What?
No,
Just the first part?
yeah.
Oh. I was impressed you did the whole thing. Everyone okay with the setup though, what I'm doing there? Nick's already working ahead here.
10, 15 for the second.
So we have 9/5 over 2/5 minus 2/5 over 3/5. 9 over 2 minus 2 over 3. No. That's a 5 up there. I wrote a 3. Hang on. I was doing the division in my head. This is 2/3, 2/5. There we go. 2/5. 5/5. Yeah, it is. It just wasn't
23
equal
over
to what I
6.
had there. What'd you say?
23 over 6.
23 over 6? So if we took these horrendous fractions that we started to list, we only listed the first 3 terms over here, and added them forever, because it would be so much fun, we would eventually end up with 23 over 6. Questions? Okay, so there's 3 big takeaways you're going to take away from today on 11.2. One of them is knowing what a geometric series is, and knowing whether or not it converges, and knowing how to find its sum. That's all one. So that's what we've been doing, right? We've been recognizing the common ratio, knowing it converges, and finding the sum. The next big takeaway is what's called the harmonic series. The harmonic series is probably one of your best tools for the rest of chapter 11 as well. And it's a very specific series. It's the series that looks like the one on the bottom of page 119. It looks like this. It looks real simple. That's it. That's the whole thing. It has its own name because it shows up so often. It's called the harmonic series. I will refer to it probably 100 more times for the rest of the semester, if not more. And the notes there just say it diverges. Diverges. I want to show you why. But you are going to memorize that it diverges, so it'll make your life easier. And this one's kind of strange. Let's list the first few terms of it. What's the first term?
1.
1. What's the second term?
Yeah.
1/2, right? I'm plugging in 2.
1/3.
1/3. 1/4. Plus sign got a little weird there. 1/5. Those terms are definitely getting smaller. They're getting smaller, but it diverges, meaning even though they're getting smaller, they're not getting small fast enough that the ones on the end don't add up to too much. They still add up. Divergence means it adds up to infinity. Even though you're adding smaller and smaller fractions, it adds up to an infinitely large number. I'm going to give you a visual and a little review from the end of chapter 7, I think it was. Remember in chapter 7, we looked at finding, say, the integral from 1 to infinity 1 over x dx. The area underneath this curve. You kind of remember doing that? Improper integrals. Do you remember what happened when we found that?
It ended up being a finite number.
This one actually ended up being an infinite number. A lot of them ended up being finite, but this particular one ended up being infinite. And I'll show you why. Jogging your memory. We took the limit as b went to infinity. 1 over x dx. Remember that? It's been a while. Chapter 7 was months ago. What's the integral of 1 over x?
Natural log of x.
Natural log of x. Evaluated from 1 to b. I'm totally in the corner here, sorry. And this equals the limit as b goes to infinity of the natural log of b minus the natural log of 1. That's just 0. But what happens to the natural log as you go out towards infinity?
Just keeps them.
It just keeps getting bigger. The natural log function's always kind of slowly kind of goes up to the right. So this part goes off to infinity, which means that that area actually was infinite for this particular function. We had other ones that were finite. We're going to talk about those next time. So this is an infinitely large area. It gets closer and closer over here, but it takes so long to get close that the further out you go, you just keep adding a little too much area. So this area is huge. It's not a finite area in this particular example. I want to compare this harmonic series to this graph. I need another color. I'm going to put the scale on here. 2, 3, 4, 5. I'll use my green, I think. What is the area of this green rectangle right here? It's the area of that green rectangle. I got the width. The width is 1. What's the height? 1, right? Because we're putting 1 into the function, 1 over 1, the height is 1. The area of this green rectangle is 1. Area is 1 for that guy. How about the area of this green rectangle? 1 times, what's the height here?
1/2.
1/2, right? We're plugging 2 into there. That's 1/2. And if I do another one, guess what this one is? 1/3. And the next one will be 1/4. So all of these green rectangles, if I add them all up, are this. Right? The first rectangle plus the second one plus the third one and so forth. All of those green rectangles add up to the same thing that this series adds up to. Tell me about the green area compared to the red area. Bigger or smaller? Bigger, right? They're all a little bit bigger than the red one. So the green area is larger than the red one. What did we just say the red one does? The red one goes to infinity. The red area is infinitely large. So what does the green area have to be? Infinitely large, even bigger, an even bigger infinitely large number, right? So because the areas of these green ones are larger than something that's infinite, that is why the harmonic series, oops, throwing things around here, diverges. And the harmonic series is going to be our example quite a bit of the time because it's a little bit mind-blowing to think, these are getting smaller. They're getting smaller, the terms are approaching 0, but they're just not getting to 0 fast enough for it to converge. A lot of us think that if they get tinier and tinier, it will always converge, and that is not the case. Okay, last little piece on 11.2. Remember I said there were 3 things you want to take away. One is the geometric series, how to find if it converges at its sum. The second thing is the harmonic series, knowing what it looks like, knowing that it diverges. And the third thing is what's called the divergence test. The divergence test has some weird notation, which I'll write up here, and then we'll put some words with it. Test for divergence. If the limit of an does not exist or does not equal 0, then the series is divergent. Now let's just talk about what that means. The contrary is not true. So what does it mean, the limit of an? In here. What's an in this case? What do I mean by the an? What is this an thing? It's not the whole series though, because see, this thing is the series. That's the series. What's the an? Just the term, each term separately. So we want to be careful because we talk about sequences, we talk about series, and the an was listing each term in sequences. It's also listing each term for series. So this says that if your terms, the limit of your terms, if they don't exist, or if those limits are not 0, then it's divergent. What was that example I made up earlier? I'm trying to remember what it was. Where it was 3 plus 12 plus 48, that one that I made up earlier?
R was equal to 4.
Yeah, R was equal to 4, A was equal to 3. We made this one up. What are my terms doing? Increasing, and what are they approaching as I go towards infinity?
Very true.
Yeah, the limit as I go to infinity for this particular series, those are just getting bigger and bigger. The limit is infinity, which means that limit doesn't exist. So if your limit doesn't exist, because they're just getting really, really huge, then we know this series diverges. Because that says if your limit doesn't exist, or if it's not 0, we'll give you an example of that in a second, then it's divergent. I'll give you an example of where it's not 0. And then you want to be really awake for what comes next because it's one of the biggest errors coming up. Here's a really interesting series. 4 plus 4 plus 4 plus 4 plus 4. I'm going to add 4 forever. What are my terms approaching? What is each term getting closer and closer to? So eventually the next term is going to be really large? You sure? Well, I think the next term is going to be 4. And the one after that's going to be 4. Well, that's the thing, that's the important thing. So this is just talking about each term, not the sum, but each term. That's the. So I'm glad you made that mistake, actually. Do you agree that if I went out here and I kept writing terms forever until I got, I don't know which direction I'm facing, all the way to New York, the next one would be 4 still? So these are actually approaching 4. Right? The terms are getting closer and closer to 4. They actually started at 4 and stayed at 4. What are these going to add up to though now, Joseph? They're going to add up to an infinitely large number, right? Because they just keep getting bigger and bigger. If you add 4 forever, you're not going to converge on anything. So this sum doesn't add up to anything because these terms are too big. I keep adding 4 forever, I'm just going to go off towards infinity. So this is an example where this is not 0. Because my terms are not getting small, approaching 0, I'm guaranteed it will diverge. So the two ways that you can tell something diverges is either your limit doesn't exist, or your limit is not equal to 0. The limit of the general term. Now the opposite is not true. What are these terms doing? Where are they approaching, these terms? They're approaching 0. Still diverges though. So it's an if-then statement. I'll give you an example. Think about it right now, make sure I say it the right way. If you are not enrolled in this class, I'll say it back to that, make sure it's a not equal to 0. Let's say it this way. So if you're enrolled in my class, then you're an LMC student, right? If in my class, then you're an LMC student, right? Agree with that statement? But the opposite's not true. If I find someone outside and say, hey, are you an LMC student? That doesn't mean you're in my class, right? It's not that it's a definition, it's one implies the other, but not vice versa. So this says that if your terms aren't approaching 0, you're gonna diverge. But it doesn't mean that if you are approaching 0, you converge. It's not one or the other. Sometimes there's LMC students other than you guys, believe it or not, who aren't in here right now. And so sometimes you can find people who are LMC students, but they happen to not be in my class. You can find series whose terms approach 0, and they could still diverge. There's a reason it's called the divergence test. It's not that it tells you it converges or diverges. What it says in my head is that to have any hope of a series converging, the limit better be 0. Because if it's not 0, it'll diverge. But if the limit is 0, we only have hope. And in this case, the hope wasn't enough, it still diverged. We're going to talk a lot more about that divergence test coming up in the next discussion. All right, your brains are about to fry, I know it. Look at example 7. Example 7, I skipped over 6 on purpose. Tell me if you think it converges or diverges.
Diverges.
Why do you think it diverges?
Because don't go to infinity.
What's going to infinity?
Like when we take the integral of this limit b approaches infinity, natural log of 7.
So you're taking like an integral like we did over here
Basically.
with the 1 over 7n. I like that idea. You're actually thinking even further than I was looking for. Can we pull that constant out front? You're totally right though, Ilya, by the way. Pull the 1/7 out front. What's this? That, which is called the harmonic series. What do we know about the harmonic series? It diverges, meaning it adds up to an infinitely large number. I wonder if you take 1/7 of an infinitely large number, if all of a sudden you get something else. No, right? You get 1/7 times something infinitely large. This goes off towards infinity. 1/7 of an infinitely large number still diverges. So you want to be looking for that harmonic series. Just like you're looking for geometric, you want to look for harmonic. Do you see it in example 6? Not quite as obvious there. I don't necessarily see the harmonic in that one. Directions just say, is it divergent or convergent? If it converges, find its sum. Remember, we just learned the divergence test, which I just erased. Because these terms right here in that previous example, those were getting smaller. What are these terms doing? What are these terms doing right here as I list them? What are they approaching? I couldn't hear what you said. Not quite. you're getting closer. Don't lose that 5 down there. In the long run,
1/5.
it's approaching 1/5. You were close. These terms are approaching 1/5. So if I list terms forever, the more I list, the closer they get to 1/5. What does that tell me about the series? It diverges. This is not equal to 0. Remember the divergence test. If those terms are not approaching 0, you're guaranteed it diverges. Only if it goes to 0 can we then check for convergence, which we're gonna do next week, because you guys have heard about this. At the very bottom of the page is just a comparison to notation for sequences and series versus notation for functions. Because we actually use the same ideas with functions and integrals as we do with series. So you can look at some of that notation later. Questions? Okay, so we're done with 11.2. The homework on this is due after the test. The plan for the rest of today is I'm going to give you a practice test. We're going to work on it. I'm going to pass back every